In this research paper titled, Monte Carlo Planning with Large Language Model for Text-Based Game Agents, authors Zijing Shi from the University of Technology Sydney, Meng Fang from the University of Liverpool, and Ling Chen from the University of Technology Sydney explore how to improve AI agents in text-based games. These games are interactive environments where players use text commands to navigate and solve puzzles, much like old-school adventure games. The paper was published as a conference paper at ICLR 2025. The core idea is to address the challenges of planning in these games, where agents need to understand language, reason about actions, and explore effectively without wasting too much time. Traditional methods, like those combining Monte Carlo Tree Search, or MCTS, with reinforcement learning, often require many iterations to work well. MCTS is a technique that builds a tree of possible actions and outcomes to decide the best move, similar to how a chess player might think ahead. But in text-based games, it struggles because it doesn't inherently understand the nuances of language or the game's story. The authors introduce a new algorithm called Monte Carlo Planning with Dynamic Memory Guided Large Language Model, or MC-DML. This algorithm combines the strengths of large language models, like those from GPT or similar AI systems, with the exploratory power of MCTS. Large language models are AI tools trained on vast amounts of text, so they excel at understanding and generating human-like language. In MC-DML, these models help by providing better language comprehension and reasoning during the planning process. Specifically, the algorithm enhances the large language model with two key memory mechanisms: in-trial memory and cross-trial memory. In-trial memory allows the model to remember and learn from what happens within a single planning session. For example, if the agent tries an action and sees a result, it can use that information right away to adjust its next choices. Cross-trial memory goes further by drawing on experiences from previous games or trials, helping the agent build knowledge over time. This way, the model can dynamically evaluate actions, making smarter decisions about which paths to explore in the game's tree of possibilities. The paper explains that this setup overcomes the limitations of pure MCTS, which might explore randomly without understanding the context. For instance, in a text-based game, an action like "open the door" might lead to different outcomes based on the game's state, and the large language model can reason about that based on its trained knowledge. By integrating these memory features, MC-DML makes the planning more efficient and effective, especially in the early stages, without needing extensive training data. Moving into the introduction, the authors discuss why text-based games are such a great testbed for AI research. They involve natural language processing and sequential decision-making, where agents must interpret descriptions and choose actions in environments that are often partially hidden or dynamic. Unlike simple games with clear rules, these have sparse rewards, meaning successes are rare, and require long-term planning. Traditional reinforcement learning agents use strategies like epsilon greedy, which randomly try actions to explore, but they often fail at foresight or understanding the game's narrative. The paper references earlier work, like AlphaGo, which used MCTS with neural networks to dominate games like Go. However, applying this to text-based games is tricky because actions are discrete text commands, and there's no built-in way to grasp language semantics. Some prior approaches, like evaluating actions based on semantic similarity, assume that if a similar action worked before, this one might too. But that doesn't hold up in more unpredictable games. That's where large language models come in. Recent advancements show that LLMs can generate initial plans quickly, even without much specific training. Techniques like reflection or tree of thought prompting help LLMs think step by step, but they still struggle with turning plans into actual actions and balancing exploration with exploitation in complex environments. The authors aim to answer two main questions. First, can LLMs improve action exploration in MCTS by leveraging their built-in knowledge? And second, how does this enhance overall performance in interactive tasks? To test this, they conducted experiments on a series of text-based games from the Jericho benchmark, which is a standard set of challenging adventure games designed for AI evaluation. In their experiments, the MC-DML algorithm showed significant improvements right from the initial planning phase. It outperformed other strong methods that rely on multiple iterations of training or exploration. For example, in games with large state spaces and sparse rewards, MC-DML could achieve better scores by using the LLM's reasoning to guide the search tree more intelligently. This means the agent could find rewarding paths faster, without getting stuck in unproductive loops. The results highlight how the dynamic memory mechanisms help the agent adapt on the fly. In one game, the in-trial memory might help the agent remember that a certain command unlocked a door earlier in the session, while cross-trial memory could recall similar successes from past plays. Overall, this approach paves the way for more efficient language-grounded planning in complex environments, making AI agents smarter and more human-like in text-based settings. The paper also notes that their code is available online for further exploration, and it's based on archive submission from April 2025. By blending the exploratory depth of MCTS with the linguistic prowess of LLMs, MC-DML represents a promising step forward in AI for interactive narratives, potentially influencing other areas like chatbots or virtual assistants that need to plan in real time.